So we're looking at the derivative, and an easier way to take the derivative than using the formal definition. And so far in this class, to take the derivative of a function, again, we looked at the limit as h goes to 0 of this f of x plus h minus f of x all over h. So we looked at derivatives of functions doing it this way. And if we had, for example, let's say f of x was equal to some constant c. So if we wanted to find the derivative of this, where c is equal to a constant, and we applied this derivative rule, we have the limit as h goes to 0. When we go in and plug in x plus h, wherever we see an x in this function, well, it's a constant, so there is no x. And so we would just put in here c minus our f of x function, which is also c, all over h. And so this is a limit as h goes to 0. Well, c minus c is 0 all over h. Well, 0 over a number other than 0 is 0. And so we're really basically looking at the limit as h goes to 0 of 0, which is equal to 0. Which makes sense because if you looked at the graph and we looked at what the graph of a constant looked like, well, y equals c, or f of x equals c, is just a horizontal line. And anywhere we chose a point on here, and we look at the average rate of change, we'd rise 1, go, well, we wouldn't rise any, we'd rise 0, go over k amount. And so our slope here is 0. Oops, sorry. F of x equals c, our slope is 0, or f prime of x is equal to 0 anywhere on that graph. Okay, so we have one rule here that the derivative of a function, and that function is equal to a constant, is always going to be 0. And we just proved it. Okay, so the derivative of a constant. So if f is a constant, value where f of x is equal to c, then we can say the derivative of f with respect to x. So one of those ways that we could write this was the df over dx. And this is equal to the derivative d of dx of our function, which is c. So that's just another way of saying taking the derivative of our constant c with respect to x. This is equal to 0. Personally, those are just different ways of writing it. I would have done it totally different. I would have said f of x equals c. Then another way to say that is the derivative f prime of x is equal to 0. But they all mean the same thing. And sometimes it's helpful to write it, this d dx, of something that we haven't taken the derivative of yet first. And we'll see that when we're looking at proving some other rules.
Quick question. The d of f or d of the function, I'm assuming sometimes they're going to write it as d of y, even though it's the same thing?
Yes.
Okay.
So yeah, exactly. So sometimes you'll see dy over dx, and they might have just to define the function as y equals instead of f of x equals. And we'll get into where we'll have functions sometimes where we can't explicitly define our functions in terms of y, so y equals something in terms of x. A lot of times we can do that, but there's going to be functions where it's going to be almost impossible, if not impossible, to get y by itself. And so sometimes we'll have to go in there and use implicit differentiation, and so we'll use this dy dx in there. But we have a while before we'll get to that. But that's where this, again, that notation will be helpful for us. And so knowing the different notations, sometimes some are easier or better to use than others. Okay, so let me jump in to the derivative. So basically here's the golden nugget. And so if we have some function f of x, and it is in the form of x raised to the nth power, where we're going to say n is a real number. Then if we want to take the derivative of this, f prime of x, and I'm writing it in Erica notation, this is equal to, all we have to do is bring our power down front, n, times our base, which is x, and we're going to subtract 1 from our power, n minus 1. So we got to just put in a couple stipulations, and we just have to say that this is true for all x when x to the n and x to the n minus 1 are defined. And this is our general power rule. Okay, that is going to make our life so much easier. So now we don't have to use this, at least a little bit. We don't have to use this formal definition. But if we want to prove this, and I'm not going to prove all of the different rules that I'm giving you, but let's just, it's nice to see some proofs. And this one I think is not too bad to follow. So let's do this. And so we know that the derivative of f of x, where f of x equals n, we would look at the limit as h is going to 0. Well, if we go back in and we plug in x plus h, wherever we see an x in here, we would have x plus h, all raised to the nth power, minus our f of x function, which is x raised to the nth power, all over h. Okay, so this is where, and I'm not going to prove this rule, but this is where if you look at a raised to some nth power minus b raised to some nth power, you can factor things like this. So we basically have something in that form where our a value, in this case, if we were using this rule, that is our x plus h minus our b value. Our b value in our case is our x. And so if we go back in and we use this rule and rewrite our numerator as this factor, things are going to start coming out nicely, believe it or not. So we have the limit as h is approaching 0 of x plus h minus x. So we're plugging in our a value here, So our a value again was x plus h minus our b value, minus our b value, which was x, all times a raised to the n minus 1 power. Well, our a value, remember, is x plus h, times, or not times, plus a raised to the n minus 2 power. Our a value again is x plus h, the n minus 2, all times our b value, which was x. And so we can keep on doing this. So plus dot, 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 where we have our a value, which is our x plus h, times our b value, which was x, and that x is raised to n minus 2, plus b again is x, raised to the n minus 1 power. Remember, this whole thing again is all over h.
This kind of looks like series just crammed in a limit.
Yeah, it is actually a series or sequence. Hold on, let me pause. Okay, so now if you look at this, that first parentheses in here, this x plus h minus x, notice that your x terms go away, which are nice. And then if that happens, we're left with this h times this whole thing. And so because of that, we can cancel the h's in the numerator and denominator. And so now when we're looking at this limit as h is going to 0, the cool thing is, notice that everything that has an h in here is going to go to 0. So this term is going to go to 0. This term is going to go to 0. This term is going to go to 0. And so if we rewrote this after we take the limit as that goes, h goes to 0, you're left with this parentheses, which is x raised to the n minus 1 power, plus you're left with this piece, which is x raised to the n minus 2. But you also have times this x right here, plus dot, 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 plus, okay, so this piece here is just a single x times x raised to the n minus 2 power, plus x raised to the n minus 1. So remember rules of exponents. Same base, we add our exponents. Well, this is just x to the n minus 1 plus, so if I add n minus 2 plus 1, notice that I get back n minus 1 plus dot, 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 and that's going to happen with every single term in here. When we do this and we add our exponents, notice that we get, this is 1 plus n minus 2, so that's the same thing as n minus 1, plus x to the n minus 1.
Ms. Nasser,
Yeah.
in the highlighted equation,
Mm-hmm.
with it says plus a to the n minus 3 times b squared. Why
Yeah.
didn't we include that?
We could have put that one in there. I skipped it just because it was getting compact, but it follows in that pattern. And so even if we had gone further and did this one, this would be a to the n minus 4 b cubed So there's some point that you just have to stop. And so I just decided not to do it with that piece.
Okay.
Yeah. And you go down until this no longer, right? This gets to 0. So if these values here were cubes, I wouldn't have even gotten that far.
Yeah.
So right here, notice that we can factor out each one of these terms has an x to the n minus 1. So if we pull out x to the n minus 1, there are n factors. This is all times n. So another way to write this is f prime of x, the derivative, is equal to n x raised to the n minus 1. And f of x was just x to the n. So we just showed, so we can do that little box. I know I've talked about that, but the little square at the end is showing that you finished proving. So we just proved the general power rule. So now, since we proved it, we can always use it. So something that's really going to be helpful in this class is to be able to rewrite things. That's just a lot of mathematics, is to be able to rewrite things so that things are simpler to do. And so knowing your rules of exponents are going to be really helpful. So let me just go over those real quick. And being able to rewrite radical expressions without the radical and rewriting them with an exponential form. So rules of exponents. So if you have the same base, so let's say b to the m times b to the nth power, remember the rule was you add your exponents. So this is b raised to the m plus n power. So that's one rule. If we had division, same base, the rule says that we can relook at this, and this is subtracting our exponent. So b raised to the m, the exponent on top, minus the exponent on the bottom. Sometimes it's really helpful that if we have a term in the denominator, rewriting it by bringing it up to the numerator. So remember, if you have 1 over b to the m, we can rewrite this as b raised to the negative m power.
A question going off of that, when we have the derivatives of like dy over dx, is since you're bringing this up, I'm assuming there's going to be like d squared y over d x to the squared or something like that.
So what's that is saying? That's saying that we're actually taking the derivative of that function twice.
Ah, okay.
And so you would take the derivative, and then you would look at what the first derivative is, and then you would take the derivative again.
Gotcha.
And we'll look at an example of that maybe today, probably, but if not, tomorrow. If you have the same, not the same base, let's say you have some base raised to some power n, and you have another base, let's say c raised to the m, and you are taking this all to some power, t. If this is the case, then we can rewrite this again, power to power. I guess I didn't do that one yet. Power to power is multiplication. So this would be b raised to the nt and c raised to the mt. So maybe I should just do that one real quick. B to the m, all to the nth, power to power, you multiply your exponents. Okay, so here's some examples why this would be helpful. So if we have, let's say, f of x is equal to 1 over x squared. Well, I can't write this, I can't take the derivative of this unless I rewrite this. So it's in the form where I have x raised to the nth power. So I can use this general power rule. But I can manipulate it by using this rule that if I have something in the denominator, if I move it up to the numerator, rewriting it with a negative exponent. So f of x then could be rewritten as x to the negative 2 power. And now when we want to find the derivative of this, so if it says find f prime of x, so f prime of x, so you're going to bring your exponent down in front. So this is negative 2 x, and then you're going to subtract 1 from your exponent. So our exponent was negative 2. We're going to subtract 1 from that. So minus 1. So f prime of x then is equal to negative 2 x raised to the, well, negative 2 minus 1 power is a negative 3 power. Oops. I probably shouldn't leave it like that. And the reason why I'm saying that I shouldn't leave it like that is because of the form I was given. So notice that f of x, it had no negative exponent. So let's rewrite this so that it has a positive exponent. So I'm only bringing down x to the negative 3. That's the only thing, that negative 2 has to stay in the numerator. So I have negative 2. So bring this down to the denominator so that I can make the exponent positive. And that should be f of x is equal to negative 2 over x cubed. Let's, before I do that, let's give you another rule. So the derivative of a constant multiple. Rule. So this says if u is differentiable, so the derivative exists. So if u is a differentiable function of x, and c is a constant multiple, then the following should hold. So if I look at the derivative d dx of c times u, okay, because I had the d dx here, it's telling me I haven't taken the derivative of this yet, of some constant times a function u. This is the same thing as saying c, and right now it has du over dx. This means that this is the derivative right here. So again, this is how the book's notation is giving you, and again, sometimes this is helpful notation, how it's written, but I would have written this a little bit differently. I would have just said, hey, if g of x is differentiable, c is a constant, let's say your function f of x is equal to c times g of x, then if I took the derivative of f of x, f prime of x, this is equal to c times g prime of x. Okay, So just different notation to say the same exact thing. And you'll notice that I like this, the G prime notation more than the ddx or dfdx. Okay, so that helps us because now we can have, if we have some constant times some x raised to a power, a real number, we can use this rule. And we just multiply that coefficient in front times whatever that power is that we bring down. And so let's say you're given that f of x, how about, is 5x cubed minus 6x to the 2/3 power plus 9x to the square root of 2 plus e. Oh, I guess I didn't give you the other rule. Darn it. Well, remember, just like limits, if I had a limit and I had a sum, I could look at the limit of the first piece minus the limit of the second piece or plus. And so same sort of idea here. And so if it wants us to find f prime of x, so f prime of x, we're using that general power rule. So we're bringing our power down front, so 5x cubed. So I'm going to keep my coefficient 5 there, bring my power down front, which is 3, x to the, so subtract 1 off of that exponent, so minus 1. And then we have minus, so looking at our next term, so we have a coefficient 6. Okay, let's not freak out because it's a fraction. Same thing, this is a real number, so it says we can bring our power down front, so 2/3. X to the 2/3, and it tells us to subtract 1 off of that. Well, I can write 1 in multiple ways. I'm going to write my 1 so I have a common denominator. So I'm going to write this as minus 3/3. And then I have plus, so my coefficient of 9. My exponent is a real number. I don't want you. The exponent is a real number, root 2 is a real number, so I'm going to bring my exponent down, root 2. X all raised to the root 2 minus 1. Well, there's nothing I can really do right there. And then last but not least, taking the derivative of e. Well, e is just a constant. And so this would be plus, and remember that was the first thing we talked about. The derivative of a constant was 0. And I didn't realize I had this other stuff in here. Derivative of the constant is 0. Sorry, this was notes from my didn't realize I brought up something I'd already written from. So let's clean it up. 5 times 3 in front of that x, and it's x raised to the five times 3, so this is 15 x squared, minus 6 times 2/3. Well, that's going to simplify. 3 goes into 6 evenly. It's bothering me. 6. 3 goes into 6 evenly twice, so 2 times 2, that gives us 4. X raised to the, well, 2/3 minus 3/3. That's a negative 1/3. And plus, well, I can't multiply underneath this radical. So this is just 9 root 2, and I can only write it in the form of x root 2 minus 1. And so we just found the derivative using our rules. So let me first bring to the other rule. And that one's really easy to prove. Sorry, like I said, I didn't realize this was in here. Darn it. There we go. Okay, so derivative sum rule. I'm just going to call it the sum and difference rule. So if u and v are both differentiable, functions of x, then the sum or difference, because I was putting both of those in there, of u plus or minus v is differentiable. At every point u and v are both differentiable. Okay, that's going to be helpful later on to know that they both have to be differentiable at that point, at each point. So at such point, we have the following. If I look at the derivative, so d dx, of something I'm looking at the derivative of finding, which is u, in our case, plus or minus v, this is the same thing as looking at the derivative dx of u plus or minus the derivative with respect to x of our function v. Another way to write this is du dx plus or minus dv dx. And so be careful because of the notation here. This is not like the distributive property, because it kind of looks like it is. And it looks like I'm kind of multiplying u times this d dx, and that's not right either. So these are functions, and that isn't true. So let me just prove that really quick. So we're going to show, let's say if y is equal to u plus x, then dy, u plus v. And I'm just going to do the plus. Then the derivative of y with respect to x is equal to du over dx plus dv over dx. Okay, so dy dx, by the formal definition, this is equal to the limit as h goes to 0 of u plus v. Well, remember, if we took the limit and it was a limit of a sum, we could rewrite this as the limit as h goes to 0 of u plus the limit as h goes to 0 of v. So limit as h goes to 0. Well, if we go in and we plug in x plus h wherever we see an x, so we can write this as u of x plus h minus u of x all over h plus the limit as h goes to 0 of this v of x plus h plus v of x, oh, sorry, minus v of x all over h. I don't think I probably should have broken that up, but it doesn't matter. So let's just rewrite this. This is the same thing as the limit as h goes to 0. Well, technically these functions, we can add these. They have a common denominator, right? This is all over h. This is the u of x plus h. I think I messed up. I think that from this point right here, I should have just done, sorry, I know I am, just do this. From this point, I should have done what I had done, and I should have just said, well, this is the limit. Let's go in and plug in x plus h, or yeah, so this would be u of x plus h minus or plus v of x plus h minus my u function, so u of x plus v of x all over h. So now if I distribute this negative to each term, this is the limit as h goes to 0 of u of x plus h. But this is the same thing as minus u of x, right? Plus this v of x plus h. But if I distribute that negative, that's minus v of x. So all I did was I just moved my terms around once I distributed that negative. Sometimes I like to turn my parentheses into zeros. And this is all over h. Well, going backwards, let's just group things differently. Let's group this like this, and let's group the v part like this. Normally we go from combining multiple fractions as a single fraction, but I'm going to go backwards and I'm going to rewrite this as two separate fractions. So limit as h goes to 0 of this u of x plus h minus u of x all over h. And then let's write the other piece plus, so v of x plus h minus v of x all over h. And then again, this is where, so I kind of went out of order, sorry. This is it where we can take the limit of each piece, and the limit of the first piece we can see is the same thing as the derivative by definition of u of x. And plus the limit of the second piece, that's the definition of the limit of v of x, derivative of v of x. So this is equal to u prime of x plus v prime of x, or if we want to write it in the notation they had it, du over dx plus dv over dx. Okay, so that's nice that we can break it up and take the derivative of multiple, each term, and using that general power rule. Unfortunately, that's not the case. If you were looking at the derivative of multiplication, so let's say you had f of x equals x times x. This does not equal the derivative d dx of x times d dx of x. And let's just show it real quick. If we just took the derivative of x is equal to 1. Derivative of x, and if I just use my general power rule, y equals x, if I bring down my power just to show it, this is y prime is 1 all times x to the 1 minus 1 power. So y prime is equal to 1 times x to the 0 power. Remember, anything raised to the 0 power other than 0 is actually 1. And so this is equal to 1 times 1. Okay, so that's why the derivative there is 1. And this, but if we use rules of exponents, if we again look at x times x, remember x times x is the same thing as x squared. And if we use our general power rule, now bring down our power, f prime of x is equal to 2x, subtract 1 from our power, we get 1. Or this is equal to 2x. So notice that these two things here do not equal to each other. So we just showed that when we're looking at a product of two things, we can't just take the derivative of the first times the derivative of the second. And so there's what's called the product rule, and you guys are going to have to wait until tomorrow before we look at what the product rule says. But for now, when you're looking at derivatives and it said maybe find the derivative of x plus 2 times x minus 3, we can't use the product rule, but we could expand this. And so we could, say, well, this is the same thing as, well, x times x is x squared. I have a negative 3x plus a 2x, which is minus x. And 2 times negative 3 is minus 6. And so now if I want to take the derivative of this whole thing, x squared minus x minus 6, using the general power rule, this is 2x minus 1. So the derivative is 2x minus 1. And I wouldn't have been able to get that unless I had expounded that until I give you the tools for the product rule. Okay, so I pretty much took all your time, so let me stop the recording.